All right, guys, let's do another single phase transform ratio question. I thought I had finished all these, but I only had two in the playlist. So let's finish off this third one, then we'll do some three-phase ratio questions. So we'll start off here with the current. It looks like I've been given the current on the primary being 1 amp. Looks like the current on the secondary is 8.67 amps. And what else do we know? We know the impedance here is 2.77 ohms. We're not sure what type of load that is, but it has a Z of 2.77 ohms. And we know that the primary numbers of turns is 260 turns on the primary. So that ratio there for the current is going to be the inverse for the voltage. You can see that these two ratios, primary voltage over secondary voltage, is equal to secondary current over primary current. They're obviously the inverse. And so this ratio, which is going to determine our voltage and our numbers of turns, is going to be the opposite. So this guy is going to be 8.67. And this guy is going to be 1. So the ratio there on the current, if we inverse that, will give us our ratio for our voltage. So we can now use that in order to find our numbers of turns, and we can use it to find our primary and secondary voltage. So let's start off with the number of turns here. Looks like we have a lower number of turns, so we can put some arrows in. Again, this is a higher value. This is a lower value, matching with this ratio right here. And then our voltages are going to be the same ratio. And obviously the currents are the inverse of that, right? So this guy has a lower current and a higher current. And that is because power in is supposed to be equal to power out, meaning that our V primary times I primary should be equal to V secondary times I secondary. Right, so if we have, in this case, a higher voltage and a lower voltage, then the power has to be the same. So our current has to be lower and higher on the secondary there. Okay, hopefully that makes sense. So now we've got our currents, and we've got, what do we need? We need to find our secondary numbers of turns. So let's do that again in blue. Anytime the arrow is pointing down, it means you need to divide. So you can do cross multiplication if you wish. But if you just put these arrows in, then this guy pointing down means you have to divide. This guy pointing up means you have to multiply. So we're going to take that 260 that we have on the primary, and we're going to divide by the 8.67, and that should give us the number of turns on the secondary there. So let's bring up calculator. Let's move this bad boy over here. There we go. So what do we need? We need 260. I always forget how to turn this guy on. There we go. Okay, 260. We're going to divide by 8.67. And that gives us 29.98. So essentially we've got roughly 30 turns on the secondary there. Okay, so now we've got the turns on the secondary. What else can we do? We could find our secondary voltage, right? Let's see, we've got Ohm's law here, and across this load right here we have 8.67 amps flowing through an impedance of 2.77 ohms. And so if we do 8.67 times 2.77, so 8.67 times 2.77, then hopefully that comes up with a standard voltage. Beautiful. So 24.0159. We're going to keep that as a standard voltage of 24 volts. Okay, so we got 24 volts on our secondary there. So this voltage right here is 24 volts. And we know that we're going to have a higher voltage. How much higher? Well, 8.67 times higher. So this value right here is going to be 24 volts on the secondary. This arrow again is pointing up, so it's telling us to multiply by that factor of 8.67. And again, hopefully we'll have a standard voltage. So I've tried to make these guys standard voltages all the way through. So 24 times 8.67, and that gives us a primary voltage of 208 volts. Excellent. So we have 208 volts on the primary. So those of you guys watching this video where you are in a different country, in Canada, we use 120/8 for most of our commercial applications. Whoa, easy now. So this voltage right here is now 208 volts on the primary. And now if we've done everything right, then our VA should be the same. So this guy right here for the VA, this is voltage times current. Okay, so we're just doing single phase right now. So these two values right here will be voltage times current. So this guy is 208 volts times 1 amp, which is obviously 208 VA. Okay, let's do the other guy. This guy for our VA or our secondary is going to be equal to 24 volts times our secondary current of 8.67 amps. And hopefully that gives us a VA of 2.8. So 24 times 8.67. Beautiful. There we go. So we got 208 for our VA. And everything has basically worked out, right? So what else do we need here? We can throw this guy in here to finish this guy off. And I think that's essentially everything we need for this question. Okay, so you can see that the voltage and the current ratios are the inverse of each other. And the voltage is always dependent on the number of turns. So if you have more turns on the primary, you're going to have more voltage. If you have less turns on the secondary, you're going to have less voltage. All right, so we're going to build on this in the next video. We're going to do a three-phase transformer. And everything's going to be based off of the phase because all these ratios that we just used were single phase values. And again, even though we have a three-phase transformer, it's made up of 3 separate single phase windings. So we'll see you on the next video, guys. Keep going on the playlist, and the next one will be a three-phase transformer where we can look at the ratios. All right, guys, thanks very much for watching. We'll see you on the next one.